to take the question in between your talk or at the end?
No, whatever. Yeah, if it is required in between also, it's not an issue at all.
Okay.
So I'll just mention that in my presentation.
Mhm.
No problem. Actually, it's okay.
Otherwise, they can write their question in the chat box, and later on we can also
Yeah.
address
Yeah,
those.
either way, it's better to be interactive, more like with.
Okay, fine, fine.
Yeah,
If it
yeah,
is fine for you, then it's no
yeah,
problem.
it's a oral, and then because I think the connectivity is also good. If there is a problem in the connectivity, then all these issues will crop up.
Exactly,
Otherwise,
exactly.
it's better to have more interactive and
Sure, sure.
yeah. So when you join partner, IT partner,
I joined in 2010.
oh,
So
that's
2008 to 2010, I worked in one of the industry. Then I joined in Patna.
okay, okay. So that time, Professor Dandapat and these people are there
Yes, yes, yes,
for building the
yes.
for
Building
the
this
at the initial
campus.
inspection time and all. Yeah, right. Yeah, the director was also the same. No, from beginning your director was there, or like at the beginning IIT Guwahati director used to take
Yes,
care
at
of
the beginning, Professor Borua was there
Baruga.
for Professor
Yeah,
Boria
right.
for year and a half. Then
Okay.
Professor Anil Bhumik came.
Okay. Oh, Anil Bhomik. Yeah, yeah, from Kharagpur only, right. So during
He
Anil
just
Bhomik time
recruited me
also, Professor Danapat was there.
very briefly. After
Okay.
that, Professor Abuti Khan actually came
Okay. Okay.
from chemistry department of IIT Guwahati.
Oh, acha, acha. Yeah.
So I think we can start now.
Yeah,
So,
right.
so
Yeah.
I welcome Professor K.S. Rao for giving us time for one session. So this session will be chaired by Dr. Sumanta Gupta, who is an associate professor in the Department of Electrical Engineering, IIT Patna. So over to you, Sumanta, sir.
Okay, thank you, Udit. And welcome to all the participants in this online short-term course on deep learning-based speech processing techniques for smart health and education systems, concept, recent trends, and key challenges. And we are really fortunate to have Professor K. Srinivasa Rao from IIT Kharagpur. Professor Rao is a professor in the Department of Computer Science and Engineering since 2007. His areas of research interest include audio, speech, and music processing. He was faculty member at the Department of Electronics and Electrical Engineering at IIT Guwahati from October 2005 to May 2007. He obtained his PhD in CSE or Computer Science Engineering Department from IIT Madras in 2005, ME in Communication Systems from PSG Tech, Bharatiyar University, Coimbatore in 1993, and BTech in Electronics and Communication Engineering from RVR College of Engineering, Guntur in 1990. He has guided 12 PhD and 14 MSy research theses and 12 ongoing PhD theses in the area of speech and multimedia processing. He has published over 300 research articles in reputed international and national journals and conferences. He has executed around 15 sponsored research projects worth around 10 crores in the area of speech and music processing. So today he will be delivering the talk on the topic detection of vocal folds disorder using EGG signal. So over to you, sir.
Yeah. Thank you, Professor, for a nice introduction. Just covering the overview of my profile in a very brief terms. It's good. Nice to, and I would like to thank the organizers of this workshop, basically Professor Udeep and his colleagues, of the other departments and all. And I would thank the participants who are attending this particular workshop. Maybe the colleagues of the department of the same institute or from other institutes as well. Yeah, I just gone through the overview of the workshop in the different sessions and all. The topics are very versatile and the talks that is offered by the eminent people across the world. Just now, the morning, just the talk before me, heard that it's from Professor Shrikant Narayanan, who is a legendary in in a particular, like in a speech, and as well in the biomedical applications and so on. So it will be nice to participate in this particular workshop as a speaker in this particular session. So without any further delay, I just want to start my presentation. So let me see. Yeah. So is my can you able to see my presentation?
Yes, sir. It is visible.
Okay. Yeah. Let me keep it in full screen mode so that. Oh, sorry. Oh, sorry. Yeah. 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 Now it's in full screen mode. So is it visible, all of you, or for the participants?
Yes.
Hello.
Yes,
Okay,
it is
yeah,
visible.
good. Yeah, right. So let me start the presentation. So as you aware that from the brochure, so the today's talk and in this particular session will be on basically analyzing the glottal activity in the context of vocal disorders. But in this particular talk, I will talk about vocal fold disorders, and prior to that, I will try to focus mainly on the what is glottal activity and how it is for in view of speech production, how it used to be, and after that, we'll see that what are the various abnormalities present in that. Due to various contexts, like vocal disorders is one of them. So that way, I'll that the talk, the organization of my overall talk will be like this. These are the broader contents of this talk, which I'm going to present now. So it starts with introduction, where I'll try to introduce the basic terminology related to glottal activity and how do we acquire that and how do you capture that, what are the different instruments related to that, and how it is related to speech production, and what is its physical characteristics, physical nature of this glottal activity, how it used to be, which are the anatomy or physical structures that are responsible for glottal activity. So these things very briefly we'll discuss in the initial 4 or 5 slides of introduction, and after that we'll go into the more technical thing, and where like how do we parameterize or how do you characterize the glottal activity. And basically the glottal activity is characterized by the significant instants that are present in the glottal signal or glottal activity, and in that characterizing glottal activity is nothing but accurate detection of these instants and all. And further in the technical content of this particular talk, where we discuss about how do you extract these instants from the EGG signal using a phase component. And then suppose the EEG signal is a bit of noisy. In that case, how do you extract the glottal instance, and what are the problems with the normal methods and all? And then finally, how do you capture these instants or acquire these instants, determine these instants in case of pathological EEG signals? That means it's not normal. Like the EEG signals that are captured or that are the collected from the patients who are suffering with some vocal disorders, the pathological diseases related to that. So in that context, how the glottal activity look like, or how the glottal activity used to be, and then how do you analyze that, and how do you capture that, and how do you extract the relevant information or key instants from that. And finally, and in that process we also try to see the how do you discriminate the various vocal disorders. And in the process we'll end up with, there are certain vocal disorders that appears to be very similar using a certain kind of parameterization. So in that case, how do you again further classify the most similar vocal disorders, which appears to be similar because of the similar physical phenomena. So these things we'll discuss over here, and then finally we'll wind up with the references and publications. So this is the broader content of my talk, and let us start with the introduction. And as I mentioned that in the introduction, I just introduced the basic the physical organs or anatomy that is responsible for this glottal activity, and then how do you capture that, what are the hardware or the mechanism to capture this glottal activity. So these aspects we'll try to discuss, and then more into the what is glottal activity, and those aspects also we'll discuss. And as already as we know that the glottal activity is nothing but here maybe actually the glottal activity is basically responsible for in the it will be nice or it will be more appropriate in the context of speech production. That means so when you are producing the speech, as we already know that the speech is produced during the exhalation of air and all. That means when you are releasing the air from your lungs, at that time you can able to produce the speech. You can try or you can able to feel that. So without exhalation of air, you cannot produce the speech. That means whenever you are speaking all the time, the air is coming out of the lungs, and that will be released through your vocal system and all. So during that process, only the we can able to produce the speech, and you can't speak during the inhalation and all. And here in the speech production, the basic glottal activity, that means the basic source of excitation will be due to the this vocal folds vibration. And these vocal folds will be here, you can see in this diagram. So the vocal folds will be here, they present here in a trachea just before the laryngeal cavity. This is the laryngeal cavity, and here in the laryngeal cavity, there are vocal folds that are kind of a pair of tissues, and so they will be like usually they will be twin folding tissues will be there inside the trachea. And then whenever the air is you are whenever you are releasing the air, and these tissues will vibrate and all. And because of the vibration, these tissues will be closes and opens. They close and open whenever you are releasing the air. So they vibrate because they are the twin tissues and all soft tissues, and they vibrate. And in the process of vibration, they closes and then again open, close, open, and all. So that opening and closing, in a regular fashion, so that creates a kind of a periodic vibration and all. And so because of that, that produces a kind of excitation, major excitation, which is responsible for producing a certain kind of sounds. Basically all the vowels and all the voices sounds are produced because of this particular excitation and all. And that way you can what that means when you are releasing the air, suppose we are not speaking anything and you are releasing the air through these vocal folds. So at that time actually here the vocal folds will be open, and then the air will be freely released and all. And whenever we are attempting to speak, at that time the vocal folds vibrate. That means the air, whatever you are releasing, so that will be chopped into narrow pulses. And these narrow pulses of this energy that will be propagated through the oral cavity. And at that time, whatever you want to speak, a particular sound unit if you want to speak, then the oral cavity shape will be controlled. Because of that, there are different vocal oral cavity shapes that are responsible for different sounds will be produced. And for them, actually, for them, the basic excitation will be these vocal folds vibration. And these vocal folds vibration, because of that, instead of releasing the air in a free flow manner, so the air will be chopped into narrow pulses, and these narrow pulses will be propagated through the oral cavity or this vocal tract system and all. And at that time, whatever you want to speak, again, that the speech is nothing but it's contributed by a sequence of sounds and all. And whatever the sounds that you need to produce, and the vocal tract will take the appropriate shape. And at that time, these narrow pulses will be propagating through that, and then based on the shape of the vocal tract, different resonances will be generated, and that contributes to a specific sound and all. So that way the sounds are produced, and then the sequence of sounds in a very close proximity, that gives you a normal speech, like words and the sequence of words and all these things together and all. So that way the vocal folds mainly contribute for production of speech. And they present in the laryngeal cavity and all. And so the vibration of vocal folds, yeah, as I mentioned already, they provokes, that means they create a kind of excitation to the vocal tract resonator, with which you can able to produce the voiced speech. And again, in the speech there are two types: voiced and unvoiced speech. Voiced speech is nothing but for the speech sounds which are produced in the due to the vocal folds vibration. Those are known to be voiced speech. Basically, all the vowels are contributed by the vocal folds excitation or vocal folds vibration. And not only that, there are other sounds also, like in some consonants, like for example, ga, ja, da, da, ba. So these sounds and all, they are also voiced and all. That means those sounds also produced because of the vocal folds vibration, along with some constriction that is provided by the vocal tract and all. So that way, the various sounds are produced either due to the vocal folds vibration or due to a constriction at a different places in the vocal tract. Otherwise, if you can't produce a sound without constraining the this exhalation of air and all. If you don't put any constraint and if you release the air, you don't produce any sound at all. You are releasing the air during exhalation and all. You don't produce any sound. If you want to produce any sound, you have to constrain that air. You have to put some constriction, and that constriction will be offered by at different points in the oral cavity as well as in the glottal cavity also, in the laryngeal cavity. And one of the constriction that is offered will be the vocal folds, because as I mentioned, the vocal folds will be closes and opens irregularly and all. So that produce a kind of a constriction in a very periodic way. So with that, whatever the air you are releasing, so that air will be transformed in the form of a narrow pulses, and these narrow pulses will be propagated through the oral cavity, and the shape of the oral cavity, different sounds are produced. You can able to experience, try to utter the different sounds like ah, ee, oo, or something like that, where you can see for all of them, the excitation is the oral, these vocal folds only, but the sounds are different because of the shape of the vocal tract and all shape, and then the different movements of various organs in the oral cavity, like tongue, lips, and so on. So that way, the speech production will be there, and then the cause for the speech production, that voice speech means, that is basically due to the vocal folds vibration. And then the properties of this the vibratory properties of vocal folds are influenced by various things. The strength, because the vocal folds are here in the laryngeal cavity here and all, and the vibration characteristics are depends upon the various factors like the strength of laryngeal aerodynamics, length of vocal folds, thickness of vocal folds, and then the muscular laryngeal tensions that is offered. So these are the various factors that influences the vocal folds vibration and all. And so here, this close up is the, like, where you can able to mark here. These are the two vocal cords, vocal folds, and they vibrate and all. And here behind that is the trachea, and that is connected to the lungs. And during the exhalation process, the lungs will release the air, and when you release the air, and here these tissues, these vocal folds, they vibrate and all. Vibrate means they come and contact. That way, this closed entire the trachea will be closed, and then beneath that the pressure will be built up, and with that again the vocal folds will not sustain that closure, and again it tries to open. And the moment when it opens, then some air will be released, and then again immediately when the air is released, then the under the below that the pressure will be reduced, and again the vocal folds will start closing. So that way again the pressure build up. So that way it's a continuous process. So with that, actually the vocal folds will be vibrating, and the starts opening, closing, opening, closing. So with that way, the air that is coming out of the glottal, this laryngeal cavity, will be released in the form of narrow pulses and all. And these narrow pulses will propagate through the oral cavity, and with that, the different sounds are produced. So this is the way the vocal folds vibrate during the exhalation of air. And here, the process of vibration of vocal folds and the transforming of continuous airflow into the narrow pulses. So this is known to be a glottal activity and all. And so this glottal activity is very important, as I mentioned, that in case of speech production. And if you want to analyze the characteristics of the speech and other things, where this glottal activity also play a very important role, because this acts as excitation. And then these narrow pulses, whatever is propagated through the vocal tract system, and whatever the response of the vocal tract system, the system response, that will be superimposed on these narrow pulses. And with that, actually the speech, whatever you are listening, so that is nothing but a superposition of or a convolution of these excitation. On top of that, the vocal tract response will be there. So that way, the outcome of the speech is nothing but the glottal activity due to the vocal folds, and then on top of that, the response of the vocal tract, whatever the shape of the vocal tract and what are the movements of various organs in the vocal tract, that also will participate, and their overall the consolidated response also will be superimposed. And that way, whatever you are listening, the speech is nothing but it's a convolution or combination of both the glottal activity and the vocal tract response and so on. Okay. And now you see that how do you capture that glottal activity? How do you capture that, or how do you visualize that? How do you analyze that? So for capturing the glottal activity, one way is that actually by using the Electro Glotograph, this is a device. You can able to see here in this particular picture, a person is wearing the this one the headphones and a microphone here, and along with that you can able to see around the neck he put some strap, and then there is some device that is connected over here. There are the electrodes. There are just some two metallic plates will be there. Those are the electrodes, and these electrodes are connected to the device, and this is electroglotograph device, EGG device and all. And here you can see here the person, suppose when he's speaking, the speech is recorded through this microphone, and then the glottal activity that is responsible for that particular speech is recorded through these particular electrodes, and where these electrodes and as well this microphone is also connected to the EGG device. So with this, you can able to simultaneously you can able to record both the speech, that is nothing but the speech that is recorded through a close talking microphone. You can able to see near the lips there is a microphone. It's a collar microphone. It's not collar microphone. It's a microphone that is connected through these headphones and all. And here around the neck there are the electrodes or the metallic plates used to be there that used to capture the glottal activity. And these two are connected to this EGG device and all. And using EGG device, you can able to connect, you can able to record simultaneously both the speech signal as well as the glottal activity. It's nothing but the vocal folds vibration and all. And yeah, related to that, here the electro EGG is a non-invasive technique to analyze the activity of vocal folds vibration, because you are capturing this glottal activity from the keeping the metallic plates or electrodes around the neck here, near the thyroid here and all, where you can able to sense the. Otherwise, if you keep the fingers and then if you try to utter any vowel, like R, E or whatever, then you can able to feel some vibration and all. So that vibration is because of the vocal folds vibration, the closing and opening of vocal folds and all. And so that way you can able to, so this is a non-invasive technique. Non-invasive technique means you are not really examining, you are not really placing the device near the vocal, into the vocal fold, into the mouth, and you are not doing that. So you are just capturing the signal, the glottal activity signal indirectly around by keeping the electrodes around the neck here near this quadrant, near the larynx. You are keeping that, and then you are measuring or you are capturing the glottal activity and all. And the way how you are doing that is nothing but you are keeping some two electrodes, a pair of electrodes here around the neck. That means near the place of these vocal folds. And the high frequency modulated current with a low voltage is passing through the electrodes. And then here, as I mentioned, these vocal folds are vibrating. That is, starts closing and opening and all. So because of that, when you are passing these high frequency modulated current through that, it captures the closing and opening of the vocal fold. That means when the vocal folds are closing, it means that actually both the vocal folds are closing. It's almost like you can feel like a kind of a short circuit or full connectivity was there. And then it just measures what is the impedance or the admittance at that particular point, because the vocal folds are opening and closing and all. At the time of closing, then the contact area will be maximum, and then you can able to record the corresponding admittance over here. And when it's opening here, then at that time you can able to offer it's a kind of open circuit, or you can able to see the maximum impedance that was there during the opening phase, and at the closing phase the impedance will be the minimum and all. So that way you can able to, the device can able to record the electrical admittance proportion to the closing and opening and all. Whenever it's a closing and all, then the impedance that is offered will be its minimum. And whenever it starts opening and all, then the impedance that is offered will be increases. And then in the complete open phase, you can able to feel you can able to record the maximum impedance that is offered by the vocal folds and all. So that way, this particular EGG device, it records this vocal fold activity, that is the vibration characteristics of vocal fold activity, in terms of the electrical the impedance and all. Because when it's closing and all, it's kind of like a complete closure where these two masses will be closed together, and at that time the upward impedance will be the minimum. And then when it starts opening and when they are fully opened, at that time there is no contact at all. So therefore the electrodes whatever you receive, that is corresponds to the maximum impedance and all. So that way, when you see the display this particular signal, the EEG signal that is captured by using these using these particular electrodes, you can able to see the signal is something like this. Here is a plot. Here there are two plots are there. The plot in the upper or in the top, this is corresponds to the speech signal. It means here, as I have already mentioned, there are two sensors are there. One is the microphone, and the other one is this EEG. That is the pair of electrodes where they capture the vibrational characteristics of vocal folds by keeping intact with the by using this particular belt around the neck and all. So here the microphone signal display will be there on the top. That means this is nothing but it's a corresponding speech signal, and the corresponding the glottal activity responsible for this particular speech, which is captured through these particular electrodes or EEG device, will be the bottom one. So these are the two things which are recorded simultaneously, and you can able to see here. These are around, roughly there are 3 cycles of the speech signal and the corresponding 3 cycles of the glottal activity also, 3 or 4 glottal activity. These are known to be glottal cycles, and whereas these are known to be normal speech signal consists of 3 or 4 cycles and all. And here you can see the difference between these two, right? So this is your speech signal, and this is your corresponding glottal activity, or you can say that the vibratory characteristics of the vocal folds in the form of captured in the form of the impedance variation and all. And here this particular signal is passing through this your oral cavity, and then when it passes through your oral cavity or vocal tract, based on the shape of the vocal tract, the corresponding resonances will be produced. Because you know the principle of the resonances during your physics, your class 8th 9th, at the time you might have studied. You have a tube where you excite the tube with a tuning fork, where you can able to see the different resonances that depending upon the shape of the tube, the length of the tube, or volume or the diameter of the tube, and so on. Different resonances you can able to observe. So here also the similar principle, where here the tuning fork, the vibrations, whatever the excitation, whatever here is, it's equal analogous to your vocal folds. Your vocal folds vibrate. So with that vibration, the outcome will be the air will be chopped off into narrow pulses, and that acts as excitation. And now these narrow pulses that are propagating through the oral cavity, and the oral cavity now acts like a tube. But now this tube is not like a uniform tube what we studied, what we come across during our classes and all. But here this tube is like a non-linear one. You can able to see that because this is with the physical one, and it's a non-linear one. And this again for analysis purpose, this non-linear tube is also can be made like a piecewise linear by keeping a different sections, and we can do that. So that way, what I mean to say is that the way the resonances are produced in the case of normal physics in the uniform tube, similar to that here also, the vocal tract will offer certain resonances based on its shape, complexity of that, and that resonances are responsible for the speech, different sounds and all. Because of different shapes of the vocal tract, you can have the different sounds are responsible for that. So that way you have a speech signal, you have a glottal activity. And now in the glottal activity here, you can see here this bottom, the glottal activity, the one cycle, within a one cycle of a glottal activity, you are represented with the different sections, like you have A, B, C, D, E was mentioned over here and all. The dotted line between A and B is the phase corresponds to closing phase of the vocal folds. That means here at the starting at the A, the vocal folds before the prior to the A, the vocal folds are in open position. And now at the beginning of A, that means from beginning of A, the vocal folds now starts attempt to close. And this closing phase will take certain amount of time. So from A to B, the vocal fold starts closing, and then the moment when you reach to the B, close to the B, that means the vocal folds will be completely closed. That means prior to A, the vocal folds are completely open. And then from A onwards, the vocal fold starts closing. And again, for closing, it will take some finite amount of time. So that is from A to B. So it starts closing. So then at the time, at the point B, where it corresponds to the complete closure of vocal folds taking place. So A to B interval is known to be the closing phase. It starts closing, and then the closing will be completed by P. And then the B to C are nothing but it's a closed phase. That means vocal folds are in the closing position, and they stay in the closing position for some time. And then afterwards, again, they starts opening. They starts because the pressure that build up below that will cross a certain threshold. And then when the pressure is more, at that time, they cannot withstand the closing position. They try to open. And that is the point where the C, where the starts opening and all. And this opening phase continue till D. So till this point, the opening will exist. That means the vocal fold starts opening, and then by the time it reaches to D, around that, the vocal folds will be completely in the open phase and all. Then afterwards, then the D to E is again the opened phase. That means the vocal folds remains open there completely, and that is the opened phase. So therefore, there are four phases are there. The two are the dynamic ones. That is A to B is the closing phase, and B to C is the closed phase, and again C to D is the opening phase, and D to E is the open phase. That means already the vocal folds are opened, and then that may happen. And here these and I see that here we are analyzing the activity within a cycle or within a glottal cycle and all, within a glottal cycle. And normally for speech analysis and all, people used to analyze the speech signal much beyond this, much more than this one. Now, they don't bother about the variations within the cycle and all. So most of the research works and all, they just take the multiple cycles, like for example, 4 cycles, 5 cycles together, and within that 5 cycles and all, what will be the activity? That's what they will look into that. And then beyond that, like taking the much more than that, like a kind of 40 cycles, 50 cycles and all. So in that 40, 50 cycles, what will be the variation? So that way people used to analyze for recognizing the sound units or for recognizing the speaker or whatever. So, but very few people are like very few attempts try to analyze the at a micro level and all, like within the glottal cycle, how the signal is manifested, what are the variations are there, because these are the primary excitation responsible for whatever it is, different sounds or different speaker voices or different emotions, whatever, all of them are also embedded here and all. But here, as you see here, this is within a cycle, and again, detecting these phases is also very difficult, and also therefore most of the works are related beyond this, and this is known to be subsegmental analysis and all. Usually, the segmental analysis will be carried out where with 4 or 5 cycles put together, and the analysis will be carried out either time domain or frequency domain. And suppose if the analysis we carried out much larger signal levels, that is known to be suprasegmental levels. It is the signal having the duration beyond that. So that way, this is your glottal activity, and this is your corresponding speech signal. Yeah, now we'll quickly move on to the later on. Yeah, this is the way you have a EGG device. With that, you can able to capture the glottal activity. And this is by using this one, you can simultaneously capture both the glottal activity and the speech signal also. And most of the times, because you see that these EGG devices have come a bit later and all, and they are not frequently used. Because if you want to use the EGG device and all, you have to properly tag the device around the neck, and you have to place it very properly. Then only the activity will be captured. Otherwise, if you wrongly placed and all, then whatever the signal that was be captured is not accurate and all. And so that's the reason that people used to analyze the glottal activity by using indirect means. Indirect means they will capture the speech signal, right, by using a microphone, that is a distant microphone or like a close talking microphone. And where from the speech signal, because the speech signal is nothing but actually here the glottal activity. On top of that one, the vocal tract response will be superimposed on that, and then that speech will be propagated through the air, atmosphere, air. And because of the air, because of this propagation through air, and again the background, also the background environment, all these also will be superimposed on that, and finally you are capturing through microphone. So to analyze the glottal activity from the speech signal means there are ways, there are lots of efforts and lots of attempts were made where you can able to get back the glottal activity from the speech signal. So because we know that the speech signal is nothing but at the different stages, different responses will be superimposed. At the beginning, you have a glottal activity, and then immediately afterwards, you have like the pharyngeal cavity and all that response will be there. And then afterwards, you have the oral cavity, that is the vocal tract. And then after the vocal tract, again, you have a air transmission media, and its characteristics will be there. So to get back the glottal activity from a speech signal, so one can able to, if you can able to model each of these things, different stages, like the response of the air, or response of the atmosphere, or background, whatever is superimposed on that, you have to remove that. Then you'll get a pure speech signal and all. And from the pure speech signal, again, if you remove the vocal tract response, then you can able to get the this glottal activity and all. So that way, people used to extract the glottal activity from the speech also, because all the time you cannot get the glottal activity, because as I mentioned that the usage of device is rare, and another thing is that you have to keep the device also very properly. Then only you can able to get the glottal activity correctly and all. Otherwise, is that from the speech you can able to get back by using approximations, by doing some inverse filtering at different levels, you can able to get back the glottal activity. And compared to that, this is a more accurate one. If you can able to capture the glottal activity directly by using EGG device, then it is a more accurate and precise. Yeah, now these are the, here as I already mentioned that the glottal activity is basically the glottal cycle, sequence of glottal cycles, and this glottal cycle is again, as I mentioned that it is consists of four phases, as I described before: closing phase, closed phase, opening phase, and open phase. In that, there are two dynamic phases are there. Those are important. Otherwise, the static phases where, because the characteristics remain stable, and closing phase and opening phase, these are the two important phases where the actual vibration characteristics will be properly reflected over there. And these two phases are like responsible, or can properly characterized by using these two instants and all. And then one is going to be glottal closing instant, other one is going to be glottal opening instant. So it means that actually here, that the beginning of a closure, that means till that point actually the glottal the vocal folds are open, and after that actually then when you are attempting to speak something, the vocal folds should vibrate. So therefore they start attempt to close and all. So when they start attempt to close, so that particular point when the starting of this closing started, so at that particular point you can see a significant change in the signal and all. So that is known to be a significant instant in the like in the glottal activity. And that particular instant is known to be like a glottal closure instant and all. It's nothing but it's an instant where the glottal closing has started. And likewise the glottal opening also, it's an instant where the glottal opening phase has started and all. It's known to be glottal opening instant. These are the instant properties, so therefore you can able to detect that with respect to the sample level accuracy and all. And this has applications in case of speech and biomedical applications. In speech, you have almost all speech applications. You can use this like the instance of GCI GOI. The knowledge of GCI GOI can be extensively used in almost all applications. You can use it: speech synthesis or prosody manipulation and speaker recognition, everything. And in case of biomedical applications also, you can able to analyze, because by using these instants and all, you can able to like further analyze the glottal cycle within that, how the closing phase and what is the duration of that, how rapid it is, and all these things you can able to analyze. So with that, the voice quality, and if there are any disorders or pathological problems in the vocal folds, even that also can be analyzed by analyzing the glottal activity with the help of these two instants and all. And here, this is a picture here shown. You can able to see that how the vocal folds are closing and all. Here, the top figure, whatever here, it is the vocal folds. They are at the opening here. They are at the open phase here, and then they starts closing here. And the top figure corresponds to the closing phase of the vocal folds, and the bottom one is nothing but the other way. It's like opening phase of the vocal folds. And here, if you look at carefully, here the top in this figure, there are the three figures were here. The first one is the pictures, the images corresponds to the vocal folds in a sequence, and then the below that, at this particular instant, what will be the EGG signal. And then in the EGG signal, again, the next one is that the below signal is known to be DEGG, that is known to be differentiated EGG signal. And this differentiated EGG signal is used to basically to determine the closing and opening instant. Because you see that this is your EGG signal, and if you apply a first order derivative on this, you will get the signal something look like this. This is known to be DEGG, known to be differentiated EGG signal. So in case of in the digital domain, the differentiated EGG signal or differentiation is nothing but taking the successive sample difference. That means you have samples here, and if you take a successive sample difference and you plot those successive differences, that is nothing but the differentiated EGG. And if you look at this differentiated EGG from this, you can able to see that there are some peaks and valleys here and all. And that means here the peaks means that corresponds to there is a significant activity is taking place at that particular instant of time. Because here this particular signal is nothing but differentiating this one, the glottal, the EGG signal. It means that if suppose if you take the differences and if there is not much change, then the difference will be small. If there is a sudden change, then if you take a successive difference at that particular point, wherever there is a sudden transition was there, so that can be observed in the differentiated signal and all. So that way, if you look at this differentiated signal, you can see that there are some positive peaks and negative peaks. And here, these sudden discontinuities, these are corresponds to like activity here in the EGG signal and all. And if you look at here, the sudden positive instant or positive peak, this is corresponds to the closing instant and all. That means at this particular instant where the glottal activity or closing phase is attempted to start. So because of that, if you look at the difference and all, you can see a sudden change in the amplitude that is manifested in the DEGG signal and all. And likewise here at the opening phase, again, there is some changes there. That change is also you can able to observe in the DEGG signal. But here the closing phase is more rapid compared to the opening phase. So because of that, the corresponding amplitudes also reflected over here and all. The closing phase is more sharper and amplitude is very high compared to the opening phase and all, or opening instant and all. So that way, these two, this is known to be DEGG signal and this is known to be normal EGG signal and all. So here, if you look at this particular figure where the sequence of the pictures and the corresponding EGG and the corresponding DEGG are here. And here, for marking this one, there is you can see a vertical line here at this EGG and DEGG. So these are this vertical line is nothing but because this is a signal, continuous signal. It's a one period and all. But here, whatever is recorded here, you can see there are 8 images are there. These 8 images means they are captured only the closing phase. You see that the complete glottal cycle itself is in terms of suppose in case of male speaker, the complete cycle itself is 7 milliseconds or 8 milliseconds. 7 or 8 milliseconds. So that way you try to see that suppose if it is sampled at 10 kilohertz, for example, if it is a 7 milliseconds means that the total cycle itself is 70 samples and all. 70 samples. And now here the closing phase is here started here at this is not yet started. So therefore for showing that the position of the EGG signal corresponds to this particular image is showing here by using this vertical line and all. And here these are the opening phase because this is the opened image of the vocal folds. So therefore the corresponding position in the EGG signal is this one. This is the opened one. And now if you gradually coming over here, it starts, it is about to close or it's closing and all. So therefore, if you look at here, at this point, the third image or fourth image where the closing has started and all. So that is the reason that you can see that this vertical line is just moving towards that. And now this is the position where the closing, this is the closing instant and all. That means closing has started here also, but the closing is rapid at this particular figure, at this particular point. That's the reason that you can see sudden instant over here. And again, as you move on, then the closing is more, that is the closing is completing. And here when you reach here at this particular point, the closing has been completed. And likewise, the bottom figure is that it's already there in the closed phase. And now the opening is started, attempted and all. So that is the reason that actually if you see these 8 figures here, the bottom images, the opening phase is illustrated over here. Initially, this is closed and all. Then it starts slowly opening and then it reaches to the open phase and all. And here the images that are captured here, you see that the glottal cycle itself is, as I mentioned, it's like 7 milliseconds or 6 milliseconds something. It means that in a second you have a vibration rate of, or rate of vibration is about 150 or 200 or 125, something like that. It means that the rate of vocal folds is 125 or 150 per second. And if you capture a normal video rate is at how much? How many? It's like 25 per second, 25 frames or 30 frames per second. So therefore, if you want to capture the vocal folds activity properly, you need to have a high-speed camera is required. That means the video camera should capture the frames at a rate of like 1,000 or much beyond that, 2,000 or something like that. Then only it can able to capture all these variations. Otherwise, in a normal video, if you capture it at 25 frames per second, you don't capture anything at all. You can see that either the vocal folds will be either closed or opened and all, because you don't see anything, because the capturing rate, the frame capturing rate is much less than the vocal folds vibration rate. So therefore here, for capturing this vocal folds activity through camera, you need the camera operating speed, or you can say that the framing rate should be much higher than the normal the glottal cycle rate and all. You know that the glottal cycle rate is nothing but your pitch, that is about 100 or 150, something like that. So if you want to capture that properly, and you want to see the distinction at the different levels and all, then you should have a very higher rate you have to capture that. So that technique is known to be stroboscopy and all. Like normal electroglottalography means you are capturing the glottal activity by keeping the electrodes around the neck. And if you want to examine these vocal folds visually, that means you have to capture that video, capture the video of vocal folds vibration. For that, people, that is not to be invasive technique. For that, the people, for that in the hospitals and all, you have a small camera will be placed in the glottis and all, and then you ask the people to utter like whatever, utter some whatever. At that time, the vocal folds vibrate, and that vibration will be captured by this small camera that will be placed in the glottis and all. That is known to be invasive technique, and so that way you can able to capture the this video, and then if you play that video, then you can able to see that how the vocal folds are vibrating and all. That way, people can see the stroboscopic captured video, and with that, people can. Sorry, one. Sorry. Hello. Yeah. Sorry. So that way you can able to capture the video corresponds to these vocal folds and all. And yeah, this is the correspondence between the opening and closing of vocal folds. Yeah, just with that, actually we just completed the overview of the how the vocal folds used to be, what is the glottal activity, how it is useful. And now we'll go into the actual thing. How do you detect the glottal activity by using this glottal instance? Yeah, we spend a lot of time. Anyway, we have enough time. We'll try to cover the other things. And as you have seen here in this particular picture, this is your glottal cycle. And as I mentioned that in the glottal cycle, the important instants are closing phase, that is starting of the closing phase, and starting of opening phase. These two are very important because they will indicate that the dynamic phases in the glottal cycle will be observed from that particular point onwards. So therefore, these two instants are important. So for analysis purpose, actually, he need to determine these two instants, closing instant and opening instant. And after that, you can able to, by using, once you have these instants, you can able to find out the other phases and all, where the closing phase will stop and where the opening phase will be stopped. So that you can easily find out from that. So therefore, here the closing and opening instants are important. Here the capturing or analyzing the glottal activity is nothing but one should determine these opening and closing instants of a glottal signal and all. And for that, actually, there are some issues when you're trying to capture that, because here you are capturing these glottal opening and closing instants based on amplitude variation, because you are taking a differentiation of that. And when you take a differentiation of that, if there is sudden change, and that will be reflected, manifested as a higher amplitude over here. Whereas other places and there is not much changes and that will be reflected as a smaller amplitude. So that way, in the DEGG signal, wherever there are peaks or valleys, so those are corresponds to the significant instants in the EEG signal and all. And this is fine as long as the signal has a proper amplitude or proper magnitude or proper amplitude it bears, then it's fine. So sometimes there is a problem here. Suppose when you are relaying, if the techniques are relayed on the amplitude based signal, as a signal amplitude based criteria, then sometimes there are certain issues because of these things, various things. One of them is the transition in the laryngeal mechanism. So laryngeal mechanism means the way you are producing the speech, the voicing mode. There are in general there are four modes of voicing and all. And when you are speaking, sometimes you are shifting or you are moving from one voicing mode to other voicing mode and all. So during this transition phase, the signal amplitude will be very low, and you can able to see some kind of a distortion in the EGG signal because of the closing will not happen uniformly and all. The closing will happen some non-uniform way. Because of that, kind of a distortion will be observed, and because of that, by using this amplitude based techniques and all, it will be difficult to find out the accurate instants and all. So that is due to the laryngeal mechanisms, transition in the laryngeal mechanism, and these things will happen very frequently during the speech production. So that way we need to take care of this one effectively. And these other two and all, they happens because of the time lag between the opening and closing of vocal folds, and similarly the uneven opening and closing phases. So they also sometimes, very few occasions, they offer a distortion in the EGG signal. And when you take the successive difference or differentiated EGG, and that produce a distortion, so with that you cannot able to detect the closing and opening instants and all. And similarly, there is a weak voicing and a transition in the voicing and all. So voice transition means, so when you are speaking, when you are speaking, like you have a syllable transitions will be there, one syllable to other syllable, and those syllables may have the different voicing nature. For example, voice to unvoiced syllable may be there. So in that case, actually there will be a problem. There will be amplitude variation, much amplitude variation will be observed. And similarly, weak voicing also. Suppose when you are at the time of sentence ending, and at the time of phrase ending and all, so where you, when you are speaking, automatically you will lower your energy, and because of that, this glottal activity also you observe very insignificant and all. So at that time also, it is very difficult to detect these different phases in the glottal cycle, or glottal activity analysis also will be very difficult and all. And similarly, the vocal disorders. These are the the above four cases are meant for the normal speech or a normal person, where the person is healthy without any vocal disorders. If people are having vocal disorders, then automatically, then by default, actually, the vocal folds itself have some problem, some physical problem and all. So they cannot vibrate in a normal way. So therefore, that imposes again the problems or difficulties in the this glottal activity and all. Now we'll try to see that how these things will affect on the glottal activity and the difficulties in extraction and all. And here, this is the figure where it illustrates here the transition in the laryngeal mechanism. If you look at here, there are two vertical arrow lines are here. And here, prior to this is one one laryngeal mechanism. And after this is another laryngeal mechanism and all. And now this is a transition. That means here there is a laryngeal mechanism. There are different four types basically. From one type to other type, it is moving, shifting during the transition. So during the transition, you can able to see the EGG signal will be something like this. And here by visual perception, you don't see much change. But when you take a difference, when you take a differentiated EGG, when you take a first order differentiation on this signal, if you look at the second signal, you can clearly notice that. So whenever this before the transition or and after the transition, if you look at the EGG signal, you can have the peaks will be prominent, and there is no difficulty in identifying the peaks and all. But during the transition, if you look at here, there is a multiple peaks are observed and all. That means at the closing or opening phase, you can have a multiple peaks are there. So these multiple peaks are because of the kind of the time of closing. The closing will not happen in a uniform way. They will be like kind of a zipper effect. That means while closing, the vocal folds will not close in a uniform way, in a proper way. So because of that, you can able to observe the multiple peaks at a closing phase. Here in this particular signal, you can see that this is a multiple peak. There are two peaks are there, like a double peak and all. So in this peak section, which peak you have to pick up? That is the ambiguity. That is a problem and all. So the same thing. And here the third figure is nothing but amplitude envelope of this particular EEG signal. So on this EEG signal, if you take amplitude envelope, you can see the signal something look like. And if you go by this, here in this case and all, the peaks are very prominent, and you can say that yeah, this particular peak is a GCI and all these things. But here in this case, there are the difficulties and all. So therefore, if you go by amplitude-based methods and all, where there are issues like transition in the laryngeal mechanisms or weak voicing and all, if you go by amplitude methods, then it gives you the inaccurate results and all. Or the detection of glottal instants will be very imprecise and very inaccurate, and sometimes you will missed out also. So where therefore, instead of anchoring around the amplitude, suppose if you take the phase component, if you take the phase component of this particular EEG signal, right, and then if you look at the phase, you see that the phase is very regular. You can see that the phase is varying from minus pi to plus pi regularly in each glottal cycle, but it is wrapping around. That means this is a phase variation in one glottal cycle, and afterwards the next cycle again it's come back and again going. It's wrapping back, wrapping down to again pi to minus pi. It's coming back and again. But if you look at this rapid phase or the phase of this particular EEG signal, you can able to see its a phase is regular and it's very stable also. Okay, even in the transition in the laryngeal mechanism also, where even though the amplitude is less, but still the phase is not distorted at all, because the reason is that if the amplitude may be less because of the lower strength or whatever, but phase is not related to the amplitude. Phase is related to the changes. That means as long as the vocal folds are closing and opening, the phase will have no effect at all. And so therefore here, if you look at the phase component and all, even though the amplitude is affected, but the phase component is not affected at all. The phase is regular, periodic. So therefore, the phase is more stable compared to the amplitude component of the signal during these occasions and all. And the same thing you can also observe in the weak voicing or a voice transition also. In case of weak voicing, for example, this is a particular easy signal in the top one, where here the sentence ending, the signal is captured at the sentence ending and all. You can able to see at the sentence ending automatically, when you are speaking, when you come to know that there is an ending of a phrase or ending of a sentence and all, the voicing will be automatically lowered without your intention at all. So at the time of when the voicing is lower, the EEG signal is also very low. Amplitude is also very low. So for this, if you want to find out the GCI or GOI or glottal activity using the differentiation, so if you apply the differentiation on this particular signal, you can see this is the differentiated EEG. The second figure is the differentiated EEG, where as long as the signal strength is higher, you can able to see the peaks, prominent peaks. But as the signal amplitude is lowering, then the signal, even if you take a differentiation also, you don't see any prominence in the peaks or valleys and all. It appears like a noisy. And so therefore, what you can conclude here is that if the signal amplitude is not significant, at that time these amplitude based methods, signal processing methods and all, so they fail. But if you look at if you try to analyze the phase, you can see that even though the amplitude is very small, it's almost negligible, but still, as long as the vocal folds are vibrating, the phase will be retained. So you can able to see that there is a stable phase which is varying from minus pi to plus pi, wrapping around till the vocal folds vibrate and all. When the vocal folds doesn't vibrate, again there is no phase component. The phase will be irregular and all. So that way here, these two examples or these two figures will illustrate the importance of the phase and all. That the phase is very stable. So therefore, if you make use of the phase for computing GCI, GOI, then they are very accurate and it will give you a very precise and more robust results and all. So now, so therefore now, whatever the signal that is captured, EEG signal. So from that we need to analyze what is the amplitude and what is the phase components and all. For deriving amplitude and phase components of the EEG signal, first of all we need to convert that into we have to make it like analytic signal, and then for converting analytic signal you need to apply the Hilbert transform. So therefore here we have this E of n is your EEG signal and H of n is nothing but Hilbert transform of this EEG signal, and a combination will be your analytic signal. And upon this analytic signal, you can able to compute the envelope or phase. So this is your envelope, Hilbert envelope, and this is your Hilbert phase. So this is the envelope and this is the phase. And now for this, based on these expressions, if you compute this is your EEG signal, and this is your amplitude envelope or A of n, whatever Hilbert envelope, and the bottom one is the phase component and all. Bottom one is the phase component. But here, when you compute the phase will be wrapped between minus pi to plus pi and all. So because of this wrapping phase, you can able to see some kind of periodicity is observed, because whatever the phase that is there in the Glottal cycle, the same thing will be repeated, because the same activity will takes place and all. And because this phase is wrapped, but we know that the phase is more stable and regular and all, even in case of the issues like transition, the laryngeal mechanisms, weak voicing, voice transitions, all the cases and all, the phase component is very much promising and all. So therefore, in this work, actually, we try to explore the phase component for detecting these closure and opening instants and all. So for that, here the problem here is that if you have a phase, it's a regular, periodic, everything is good. But the problem is that the phase is wrapping. That means here, after you reach here, and again it's wrapping down, or it is going down, and again it started doing. So because of the wrapping phase, actually here, there's a sudden discontinuity is offered here at the end of each glottal cycle and all. So because of this discontinuity, the other discontinuities in the phase are like masked, because this is the major discontinuity, almost like it is varying from pi to minus pi. And whereas the entire signal is varying from minus pi to plus pi here. And after that, again, there is a sudden transition. So this transition, abnormal transition, it will mask the variations that are present within the glottal cycle, phase of the glottal cycle and all. So therefore, as long as this particular discontinuity was there at the end of a glottal cycle, it masks the significant events that are there in the glottal cycle, because we know that the significant events in the glottal cycle are closing phase and opening phase, because those are the dynamic ones, right? So those significant those events, they are like masked under this particular transition and all. So therefore here therefore, yeah, this is the overall block diagram for computing GCI GUI. We will appreciate this at the end. So therefore we are not going to discuss now here, because this is the overall thing. And yeah, before that, yeah, what I want to conclude here is that the phase is more stable compared to the amplitude component. But the phase, the problem with the phase is that the wrapping around minus pi to plus pi and all. So because of this wrapping, the actual the information that is there within the glottal cycle, so that is masked, that is not stands, or that is not observable at all under this particular transition and all. So now we'll see that how do we can overcome that. The one way is that you can able to unwrap that. That means whatever this discontinuity was there, that discontinuity will be taken care by unwrapping that. It is nothing but whatever this glottal the phase component in a cycle, you are cumulatively adding that instead of by removing this discontinuity and all. That is known to be unwrapping of the phase. We'll see that how do we do that. Yeah, before going to that, the EGG signal that was normally captured by using these electrodes, using this EGG device and all, that is a kind of like some kind of a pre-processing is required, because when you keep the EGG device here, because of the neck movement, or because if it is not placed properly, or because of the muzzle movements here and all, along with the EGG, it also captures some low frequency component, because the muzzle movements are this movement of head. So these things are like very small, very low frequency components. So therefore, when you are capturing the EGG signal, because of these additional artifacts, so that also embedded in the EGG signal, whatever is captured and all. But for analysis purpose and all, we need to remove all these artifacts and all. So for that purpose, what you are doing, because luckily these are the low frequency components. So these low frequency components can be avoided by designing appropriate high frequency filter, where the cutoff is 30 hertz, 30 or 48, so that all these low frequency components will be smoothed out, so that you can able to get the signal something like this. And now here, still in this particular signal, our interest is that only these portions, only these portions wherever the activity was there. And so therefore we can able to get the proper EGG signal by using some appropriate techniques, because this signal is almost very clean, and by using some energy based techniques or averaging techniques and all, you can able to use appropriate windows, so that you can able to nullify the effect of this that we need to stand out, we need to compute the glottal activity only during the voicing regions and all. So that way, this is again the rapid phase and all, and we want to analyze the phase only during the voicing regions. So therefore, here what we have done, we apply some energy threshold and all. Based on energy threshold on this signal B, you can able to get the signal E and all. So this is the pre-processed EGG signal. Now it's very clear and all. During the voicing regions, you have the phase is there. You have a EGG signal, and during unvoicing, there is no signal at all. And now you need to this pre-processed signal will be analyzed. So from this pre-processed signal, what we'll do, we know this is your ECG signal, and this is your rapid phase. And as I mentioned, that this rapid phase creates a problem because the transition in the wrapping at the end of each cycle and all, this is a major discontinuity. And with this effect, the actual significant events in the glottal cycle, they are masked. They are not observable at all. That's what here. The rapid phase is a discontinuous in the form of jumps of 2 pi. As a result, the discontinuity is present in the GCI GOI locations. They are not observable at all. So therefore, what we'll do here is that we'll avoid these discontinuities so that we'll make the phase unwrapping. So phase unwrapping is nothing but the phase that is actually offered by the glottal cycle, they will be cumulatively added and all. That means wherever the discontinuity was there, that discontinuity will be taken out. So that is nothing but we are taking a successive difference on this rapid phase. And in that, when you're taking a successive difference, whenever you will get a major discontinuity, at that time, you take care of that one. That means you remove this discontinuity. That is nothing but you add 2 pi at that particular instant and all. So likewise, if you keep on doing, this rapid phase will be transformed into unwrapped phase. So this red colored one, this plot, the third plot, the bottom plot is nothing but unwrapped phase of that. And still in this unwrapped phase now, you have a discontinuities that you can see in the next slide. Yeah, this is your EGG signal, just 2 cycles, just for illustration purpose, 2 cycles. And in these for these two cycles, you have the rapid phase will be there, as you have seen earlier. And now if you make that rapid phase to unwrapped phase, now this unwrapped phase will be something like this. So this is the unwrapped phase corresponds to these 2 cycles, these 2 EGG cycles and all. And as we know that each EGG cycle will offer a phase change of minus pi to plus pi. It means total 2 pi. So since there are 2 cycles are there, so the cumulative change variation in the phase will be 4 pi because this cycle will offer 2 pi, this offers 2 pi. So therefore, if you look at here, the total change, the unwrapped phase of these 2 cycles will be starts from 0 to it will go up to like close to 13 or whatever, because there are 4 pi variation, 4 into 3.14 or something, it's close to about 13. So this is the way you can able to unwrap the phase. Now after you unwrapped, you can able to see a slight changes in the phase and all. And to get to derive these particular changes, what you can do, you can differentiate this unwrapped phase. When you do that, you can able to see the signal something like this. Here the plot C is nothing but differentiating this or applying the first order derivative on this unwrapped phase. So when you do that, wherever there is a change in the phase, sudden change in the phase, so those things you can able to reflect, those things you can able to observe here and all. Whereas earlier, these things are not observable because these are discontinuities are there. In addition to these discontinuities, at the end of each cycle, there is a sudden or a major discontinuity was there. Because of that sudden discontinuity, these smaller discontinuities are not observable. And now we have removed that by adding 2 pi, by unwrapping that. So therefore, the unwrapped phase signal contains the discontinuities only due to the glottal events and all. That is the GCI and GOI. And now if you look at here, this particular signal, plot C is nothing but applying a derivative on this unwrapped phase. If you apply derivative on this unwrapped phase, you can able to see the wherever there are significant changes in the phase is there, that is reflected over here. And these are corresponds to the major change corresponds to GCI, and the lower change corresponds to GOI and all. So yeah, that way now by unwrapping the phase and afterwards differentiating the unwrapped phase, you can able to detect the GCIs and GOIs. And you can able to see now here, this is your EGG signal. And then after taking a rapid phase, then unwrap it. And then after unwrapping that, if you apply a differentiation, first order derivative, then this is the signal. This is the first order derivative of the unwrapped phase of this particular EGG signal A. So here you can see the major peaks and the smaller peaks are there. But here the major peaks and all you can easily identify. They are very much dominant within the glottal cycle. So therefore, these major peaks and all with a simple techniques, you can able to identify these major peaks and all. And here these blue vertical bars are nothing but the corresponding peak locations and all. And these are the major peaks. And now the bottom figure is nothing but the differentiation of EGG. Normally, the most of the EGG, most of the techniques to compute GCA and GOI, they follow the amplitude-based techniques. It means that whatever the EGG signal is there, just they apply the differentiation of that, and then you can able to see the peaks and valleys and all. So, and in that also among the GCA, GOI, GCA is very important because that is the closing phase. That is the responsible for generating the narrow pulse and all. So therefore, that is very important. Where during that time, the signal to noise ratio is also very high in the normal speech signal. So therefore, compared in these two instances, GCA and GOI, both are important, but among these, GCA has a more prominence because the main reason is that at the GCA, around the GCA, the signal having very high signal to noise ratio, and so therefore that is a more prominent, and most of the characteristics are embedded in that. So that way here you can able to find out the GCIs and all using this method. That means you can unwrap phase and then taking a differentiation of that, you will get the major peaks, and you can able to identify the major peak, detect the major peaks where these are the locations, and these locations are, you can see that they are coincide with exactly the peaks of the DEGG, and so that way you can able to identify the GCI locations and all. And there is no problem as long as the signal amplitude is fine. Then the GCI's detection using the DEG, using normal differentiation of the EGG signal will give accurate thing, no problem at all. But the problem is that if there are issues, then then these peaks are not prominent, or these peaks you will get double peaks as I observed in case of transition laryngeal mechanism. There the problems will be there. And now you can see here this way you can able to compute the GCA. And now how to calculate the GOI. So GOI is nothing but these are this peak, but this peak is not as prominent as this one. And one reason is that this peak is not prominent because since this peak is very high, so because of this peak amplitude is not, you cannot realize this amplitude, or you cannot able to observe this amplitude dominantly because of this. The same thing in the case of rapid phase, because of the discontinuity in the phase at the end of a glottal cycle, you cannot observe even the GCI GOI locations and all. So that is the reason that we remove that discontinuity by making the phase as the unwrapped one, right? The moment once you unwrap the phase, then that is,
Sir,
yeah.
sir, actually there is a question. Can you take one
Yeah,
question
yeah,
in
please.
between?
Yeah, please speak.
Yeah, actually there is a question from Ritujoy Bishwas.
Okay.
So he has asked, sir, what is the time frame for applying this unwrapping? Since the speech will consist of words of varying length, that is, the voiced segment would not be fixed along a speech sequence.
No, yeah, I understand. Here, the time frame or the time frame that will be applied for unwrapping will be at a sample level, sample resolution. At every sample, we'll try to do the unwrapping, because you see that you have a signal using the Hilbert transform, and this one you will get both Hilbert envelope and the Hilbert phase you will get. So therefore, the phase is also with respect to each sample. You are expecting some phase component, some phase value will be there. So, and then phase unwrapping is nothing but actually you are computing a difference between the phase, that you are taking a first order derivative on the phase. So then you can able to see a changes in the phase, and wherever you have a significant change, that is the change of order of 2 pi, that indicates that actually that is the end of a glottal cycle. So the phase wrapping is taking place. So to for that purpose, actually at that time you can able to see significant change. So therefore, to accommodate that, you are adding 2 pi to that, so that the unwrapping will take place. So the answer is that actually here the phase unwrapping, for doing that, we are doing at a sample level. We are doing at the sample. Otherwise, actually, we don't know that actually at what instant exactly the phase wrapping is taking place. So therefore, if you do at a sample level, then you can come to know that at a particular difference, if it is a very significant, at that time you can say that yeah, this is the instant where the wrapping is taking place. So therefore, we need to do the unwrapping. Okay.
Okay,
Yeah,
thank you, sir.
thank you. yeah, this is the way you can able to find out the glottal closure instance. And then, as I mentioned, as long as these closure instance are there, they are very dominant. So in the dominance of that one, you cannot realize, you cannot appreciate the peakiness or the peak due to the open phase, right? So therefore, the way we have done in unwrapping way, the same way here also. Suppose somehow if you can able to cut off these particular peaks, the peaks due to the closing, then these things will be stand out. So that we are doing here. And here what we are doing here is that this is your the here what I'm the first plot is the EGG signal, the second plot is the wrapped phase, and the third one is nothing but the differentiation of unwrapped phase. That means after unwrapping this one, again if you apply a differentiation, then you will get a signal like this. And now these are the dominant these peaks, the dominant peaks are nothing but due to the closure, glottal closure. And now our aim is that you have to remove that, because otherwise under these the other peaks, the peaks due to the or the significant events due to the opening phase is not clear, is not observable. So therefore what we are doing here is that actually from the rapid phase, we know that the rapid phase is varying from 0 to positive to negative and all. So therefore here we know that this closing phase will usually get here between this interval and all, between the this zero crossing to between this zero crossing in the middle. So because here the almost like half of the phase will be taking place. So we know that actually the closure peak will be definitely between these two zero crossings, right? Otherwise, no, you need to again you have to find out this instant, and again there will be some kind of like hyperparameters you have to take, like what is the width and how much you have to nullify. So to overcome that, here what we have done is in the rapid phase here, wherever the zero crossings are here, that means the beginning zero crossing and the middle zero crossing and all. So between that, definitely the peak will be there. Definitely the closure peak will be there. So we want to nullify that. So therefore, here all the values of these particular ones will be made it as 0 and all. So the moment once you made it 0, all of these values and all, then the rest of them will be stand out. That means the other signal will be stand out. So because of that, you can able to see the signal something like this. And now in this signal, whatever the peaks are there, these peaks are corresponds to the opening instant and all. So that you can able to see here this opening instant. Yeah, here the same thing, just same plot. These are the opening instants. And so these opening instants you can able to see if you very clearly, keenly observe the EGG signal. And in the EGG signal itself, you can able to see some change and all. Here up to this point, the closing, the closed phase, and here the opening. So because of that, there is some change that is manifested in the signal and all. So that is very clearly see in the phase. And you can see here, these are the locations corresponds to opening phase and all. And these are the opening instants and all. And the same thing you can also observe, this is the differentiated EGG, and you can able to see the peaks, the valleys here and all. They almost coincide with the valleys and properly. And yeah, here there is a problem. Here, if you take the normal DEGG and all, you can see here this valley is not very prominent and all. You can see here and all, but certain cases and all, this valley is not prominent. It's almost like a very distorted thing and all. It will be there making a decision about which point is the actual opening instant is a problem and all. Whereas here, if you go by phase method and all, you can have a prominent phase change you can able to observe. So with that, you can able to make out or can able to clearly identify the opening instant and all. So this is the overall procedure for finding out the glottal closing and opening instants in the by using EGG signal, by using a rapid phase. And this is the one of the case issues I have mentioned earlier. Like in case of weak voicing, for example, you can see that voice is weakening, voice weakness, the weakening of voice you can able to observe here and all at the tail end and all. And so whereas if you take the phase component and then the rapid phase, and then if you take a first order derivative, even the signal is very weak also, you can see that the phase component or these peaks and all, they are almost like the same dominance you can able to see, because the phase is not distorted, right? Because of that, you can able to, there won't be any distortion. Whereas if you go by amplitude based method, the last plot, whatever you can see here, you don't see much. Almost the signal is very weak, and then you cannot see the peaks prominently and all. And whereas here the proposed method based on the phase, rapid phase, where you can able to see the signal, there won't be any distortion at all. You can clearly notice, you can clearly identify the glottal closure and opening instance very accurately and all. So this is the over that way you can able to detect the open and closed phases and all. And yeah, now you can able to see the diagram, the flow chart, whatever I mentioned here. So this flow chart contain all these whatever the steps, whatever I have mentioned here. Pre-process that, then afterwards you need to unwrap that. Then after unwrapping, first order derivative. In the first order derivative, what are the peaks are there? You can first you compute the GCA, and afterwards you cut off the GCI. Then you can able to see the GOI. So these things are illustrated here. And anyway, these proposed method is evaluated using the standard databases. Like one is the CMU Architect database, Upload database, SAM database. These are the databases where you have the both speech and the EGG signals are available, and ground truth is also available. And you consider these databases for evaluation. And for evaluating these GCA detection, GCA GOI detection, these are the standard objective measures and all. Hit rate or known to be identification rate, both are same. Hit rate means actually here within a cycle, whether you can able to get one GCI or not, one location, one instant or not, whether you can detect one instant or not. Wherever the position, that is immaterial. If you can able to detect only one instant, it means that you are hit rate. That means you are identify the instant and all. But that instant may be deviated from the actual location. That may be a different thing. But the hit rate indicates that in the glottal cycle, whether you can able to observe, whether you can able to predict one instant, that is known to be hit rate. Miss rate means actually in the glottal cycle when you are analyzing, if you are not able to find out any instant, or if you say if you are not able to locate any instant, that indicates the miss rate and all. That's nothing but even though there is the instant, but you are missing, your method is missing. False alarm rate means the other way, like instead of one instant, if you can able to identify the multiple instants within a glottal cycle corresponds to two GCAs or whatever. So in that case, it's not to be false alarm. It's not to be false alarm and all. So these are the three parameters. Hit rate, it's nothing but if you can able to detect only one instant, either GCA or GOI, it's not to be hit rate is satisfied. Miss rate means somehow if you miss the instant, even though it's a glottal cycle contains the instant, it's not to be miss rate. And false alarm is that actually if you predict more than one, it's not to be false alarm. And timing error is nothing but actually when you're finding the hit rate, you are detecting one instant, but that instant may be deviated from the actual location. That means there will be some timing error and all. So that timing error is analyzed by using the distribution and all, the mean and the deviation and all. And the proposed method is compared at that time with the state-of-the-art sigma method. And so these are the evaluation. And I'm not going through the numbers and all. Here you can see that the proposed method is offering the better figures, objective measures compared to the at that time the state-of-the-art method and all. So these are the hit rate, and this is a timing error. The timing error is again analyzed because for every cycle you have a timing error. So that will be analyzed by using statistics, first order, second order statistics and all. So it means that the timing error of 0.2 millisecond means the actual the predicted instant, the proposed the detected instant is in the average sense it is deviated from 0.2 millisecond. 0.2 millisecond. 0.2 millisecond means in terms of sample number, suppose your sampling rate equals to, for example, 10 kilohertz. It means that for every millisecond, there is about 10 samples are there, right? For every millisecond, you have 10 samples. So 0.2 millisecond means there are two sample differences are there. That means the deviation is the two samples with respect to the given sampling rate. And so that is the indication of that way you can able to evaluate the methods. And again here in this particular in the databases itself, we carried out the evaluation in a very specific way. One is that the normal way of carrying out the evaluation, and the other one is that in the database itself we'll try to find out, we analyze the abnormalities or vulnerable cases. Where is the vulnerable case? Vulnerable case is that, as I mentioned, like in case of voicing transition or a weak voicing or a laryngeal mechanism transitions where the signal amplitude will be very much lowered and all. So where at that time where most of the methods will be failed. So therefore we particularly analyze those abnormalities or those vulnerable cases as TLM means transition in the laryngeal mechanism, end of voicing. These two cases we personally we like case by case we analyzed. That means we analyze the database using appropriate manpower. we identified those cases, and approximately around 300 utterances of these abnormality, these vulnerable cases were piled up, collected, and they were analyzed and all. So in this case also, we can able to see that the proposed method has a significant difference compared to the existing methods and all, right? Yeah, this one. Then coming to the noisy, yeah, then quickly I'll go to this noisy case. Almost the time up. Just another 5 minutes, I will wind up. Okay, is it fine?
Yes, sir.
Yeah,
Yes,
just five
yes.
minutes. Just introducing this one.
Okay.
Yeah, in case of noise, actually, in the EGG signal, usually EGG is captured by using electrodes. So usually the noise will not be coming to the picture. But as I mentioned, that improper placement of EGG device, and the movement of head and neck and these muscle movements and all, that adds noise and all. That adds noise. So this noise will be added, and this noise will be like a kind of random noise. And if you try to analyze this, what will be the effect of this noise on the proposed method and all? This noise will create a problem when you are estimating the phase. Also, the phase distortion will be there, and when you try to use the previous method, whatever on this noisy EGG signal, it end up with the inaccurate or improper results and all. So therefore, what we have done here is that we use the method known to be like a TVD, total variation denoising filter, where the idea of this particular filter is nothing but it tries to retain the original discontinuities, whatever is there in the signal, they try to preserve, and other variations that are superimposed on the signal, so they will be smoothed out. So here, because of these neck movements and other muscle movements, or sometimes the improper testing devices and all, they also introduce some noise, and these electronic components and all these noises will be added on the signal and all. So that signal, the noise will be approximated as like a white Gaussian noise. So we added that noise, and then we try to see that by using this TVD filter, by applying on that, you can see that this is your EGG signal, and this is the simulated one, that is noise that is superimposed on that, like about 15 dB or whatever. And then when you apply the it's a clean signal. When you apply the normal differentiated EGG signal, where it's a clear, because since it's a clear signal, where you can see the peaks and valleys properly. And but when the signal is noisy, if you apply the DEGG on that, you can able to see that the outcome, the signal is very much noisy and all. You cannot make out anything. That means if you apply the normal way of amplitude based approaches and all, in case of noisy, it completely vanished. You cannot see anything at all. So here, if you apply the like TVD filter on this, TVD filter on this, so you will get the outcome of a TVD filter will be like this. Here, this corresponds to here the discontinuities. Here, this is one discontinuity. This is the major discontinuity. So according to these two discontinuities, here you can, it shows the peaks and valleys. And whereas in the case of noisy signal also, since there are this signal on top of this one, the noise is embedded. So because of that, when you apply a TVD on that, whatever this noise, the random noise that is superimposed on that, so that will be clearly smoothed out, and the discontinuities, whatever is there for that, accordingly it will give you the peak and valley. That means if you look at the TVD applying on these two signals, you can able to see almost like outcome will be almost very similar and all. Because here this signal is nothing but just whatever the noise is there, the noise imposed the EEG signal and all. And if you apply a TVD properly by using the appropriate hyperparameters and all, you can able to properly, it can able to derive the actual discontinuities that are there in the normal DEGG signal and all. So you can able to see the peaks corresponds to the GCI, and the valleys corresponds to the GOI and all. That you can able to see here. This is a block diagram to perform that steps. So this is the signal. You can see that this is your signal. This is your normal EGG signal. And if you apply the TVD on that, this will be your TVD. And on this TVD, you can see the peaks and valleys there corresponds to it nicely. The reflects the GCI and GOI and all. So this is for the clean case. The same thing what we observed is that even if the signal is noisy also, on the noisy DEGG, if you apply the TVD, still you can able to find, you can able to detect these GCS, GOIs very accurately and all. So whereas if you apply phase and all, you can able to see certain distortion if the noise crosses certain threshold and all. So that's why we apply the TVD signal on a noisy case. where you can able to see almost like very good performance. You can see here and all. These are the state-of-the-art methods that time for detecting this one. And here, the proposed method is tested on these methods with the different noise levels and different SNR values and all. You can see here as the noise is increased, the all other methods and all the degradation is significant degradation is observed and all. Whereas the proposed method, almost you can able to see that the degradation is not at all appreciable, not significant at all. Almost like it, even at 5 dB of SNR also, you can able to see that the identification rate of 90% and all others also, it's very reasonable figures and all very accurate and robust method. So the same thing we have shown in the form of plots and all. And the same analogy, the same thing we applied on the vocal fold disorders also. Here, these are the vocal fold. This is the normal one, and these are the 5 different disorders: nodule. This is a polyp, nodule. This is a vocal folds with paralysis and other things and all. And on these signals, if you apply this was the database what we have collected in our hospital and all with the help of a Dr. Sanjeev Gupta. He used to be come to regularly to our hospital. From there, we collected this data and all. On this data, we applied this TVD and to detect the GCS and GOIs and all. And what we observed is that the TVD application of TVD can give the accurate GCS and GOIs, which are almost very much coincident with the manual efforts and all. So all these things are this one you can able to see these. Anyway, I'll share the slides and later on you can go through that. So if you look at here in the proposed method where the identification rate, miss rate and all, they are very much superior compared to the existing methods and all. The most close method is the VMD, that is a variable mode decomposition method and all. So that is somewhat reasonable compared to the other methods and all. So yeah, you can see. And then for the classification purpose, what you have done is once you detect the GCA and GOI, you can parameterize the glottal activity using these coefficients: closed coefficient, open coefficient, speed coefficient, jitter ratio and all. So these are nothing but this is your GCI location and this is your GOI location. Once you have that one, you have a time period between the GCI and GOI known to be closed phase, and this is known to be open phase, and this is the total period, glottal cycle. And using those things, you can derive some parameters known to be, these are standard parameters and all: close coefficient, open coefficient, speed coefficient, and jitter and all. Jitter is nothing but how the pitch is varying between the successive cycles and all. Because the TP is nothing but total period for a different period, different successive cycles and all. Is there any variation in the successive cycles or not? If there is any variation, then the numerator will be larger. Then you'll get a jitter will be more. Otherwise, if there is not variation, ideal case, the jitter should be 0, right? So that way you can have these parameters. Here, the important thing is that the accuracy of this estimation of parameter, this is important. And when you get these more accurate parameters, once you can be able to compute this GCI, GOI accurately, then you can get the corresponding time phases very accurately, then automatically other things will follow. And now when you analyze these, after detecting these parameters, when you analyze these parameters with respect to the multiple disorders, you can able to see that there is a clear discrimination is observed between these various disorders and all. Here, these are the various parameters, and we extracted the parameter for every cycle, and then we derived the statistics, first order and second order statistics, right? And then these statistics itself is showing the clear discrimination and all. Here, among these, the polyp and nodule, the parameters are almost similar, and others and all, they are discriminative. So therefore, from these 5 disorders, you can able to discriminate except polyp and nodule, because they will be very much confusing, because if you look at the parameters also, they are very close. The proximity is very less. They are very close. And whereas others and all, you can able to discriminate either by using combination of parameters or like even the individual parameters also you can able to, because if you look at the jitter, by using jitter itself, you can able to discriminate cancerous and paralysis with respect to rest of the 3. You can see the jitter for others and are very small, and whereas for cancerous and paralysis, the jitter is very high. It means what it indicates, the jitter is high means the successive pitch cycles and all, the variation is more. That means the duration of a glottal cycle, it's not uniform. They are varying. A lot of perturbations are there in case of cancerous and paralysis patients compared to the other patients, other vocal disorders and all. So that way, by using the jitter itself, you can able to discriminate these things. And likewise, using the different coefficients, you can able to discriminate the different ones. But the polyp and nodule and all, they are very close, because because you see that the difference between those two are, you can see this is the polyp and this is the nodule. Both of them have the growth. In one of them, the growth is symmetric. Both the places, both the vocal folds, you can able to see this problem. Whereas in case of polyp and all, you can able to observe this abnormality in only one of the vocal folds, either here or here. Whereas the nodule and all, you can able to see both. And because of this similar nature of this physical structure and all, you can, if you look at the parameters, and the parameters are very close. So therefore, what we have done here is that the parameters are similar, and because the pitch and other things are similar. So the only way is that if you analyze the entire activity, glottal cycle, complete cycle, the way it is varying and all, they are different, because the polyp and they are different. So we'll try to analyze that by using a Hilbert plot. We have done that. So using a Hilbert plot, you can able to discriminate this. So these are the statistics related to the Hilbert plot, and using that, you can able to discriminate this polyp and nodule. So that way, you can discriminate these two disorders, which are very ambiguous, by using the normal parameters and all. So now I can stop here at this point. These are the corresponding statistics. Sorry for delaying the lecture by 5 minutes.
No, sir. It's okay. Okay, sir.
Sorry, I spent a lot of time on the introductory portion actually. But I felt that that is important to later on to analyze the signal behavior and other things. So, but anyway, it's okay. So anyway, I will share the slides and also one can, and the later on, these are the publications that are coming out of this. Actually, we have started this analyzing the phase by first initially one MS student has started this named Sunil Kumar and he simulated the vocal fold activity by knowing the phase and other things. And later on, another PhD student started this, and he has extended this to the vocal folds disorders and all. His name is Tanumay Mandal. He's a PhD student. He's about to submit his thesis and all. And there is another student you can see somewhere. Yeah, Sunil Kumar. He did his MS with me, and he has started this phase as the component for analyzing the glottal activity and other things. And so you can see these publications and they are available openly. And these are the set of references and all. So thank you. So if you have any questions.
Yes, thank you, sir. Thanks for this elaborate and nice talk.
Yeah.
So, participants, if you have any questions,
Yeah, sorry, I not
please
maintained
ask.
the time. One thing, and
It's okay, sir. This is the last
yeah,
session,
yeah.
so we have some
Oh,
flexibility.
okay, good. Yeah, thank you.
So, any question from participants?
Yeah, and another thing, the implementation details and all those things and all, they can contact the PhD and MS scholars, which are there given in the publications list. Okay, yeah. Yeah, any questions? Any more questions? Okay. So then,
So,
if
sir,
there is,
I have one or two
yeah,
question,
please,
although
please.
I am not from this field, but
Okay,
still.
okay.
Sir, you said that you need EGG signal to identify some abnormality in the vocal cord.
Correct.
So is it not possible to identify those kind of anomalies just by looking at the speech means voice signal?
Yeah, that's what. Yeah, you can do that. As I told you, from the speech signal itself, you can able to do that. But the problem with that is that you can do that definitely. But the problem is that from the speech, if you want to actually look at the glottal activity, how exactly the vibrations and vocal folds are vibrating, or if you want to look at that, you need to extract again a glottal activity from the speech by removing the additional components that are superimposed on the in the process, because the glottal activity is the first one, that is the initial starting point of the speech, that is excitation. And then afterward, this excitation is passing through different cavities. One cavity is the pharyngeal cavity, that is just before the oral cavity, and then afterwards the oral cavity, the major one, which is responsible for all these resonances of the speech. And then afterwards there is a air medium, that is atmosphere, where the pressure variations are passing through, and finally reaching to the microphone. So the microphone, whatever is captured, is nothing but it's like superposition of multiple responses. So from that, we need to remove all these things. If you properly model them, then you can able to remove it. But modeling these things are a bit complex and all. So even though if you remove, in the process of removing, you will lose some of the glottal information or glottal cycles. Sorry, glottal information. That is the problem. That's why, whereas if you can able to capture directly this EGG signal, so yeah, it means that you are capturing the more accurate the information, because you are directly capturing the EGG. And again, it's EGG also. Again, the effect of vocal tract will be there, but that's not that much, because when you are capturing that, whatever the vocal tract resonances are there, some of the resonances that will also hit the glottal activity, or that also observed in these vibrations at the vocal folds also, but that effect is less. So that way, if you have the EGG signal, that will be the more accurate and all. And anyway, people now computing back from the voice signal also. And again, in the voice signal also, you can have that, you can able to discriminate that by using these vocal fold disorders and all. But the thing is that here, using a glottal activity, you can have like one-to-one kind of a correspondence. You can able to, what is the physical limitation, what is the physical problem in the vocal folds, because of that, why the vibration is not proper, and how it is actually reflected in the signal, and also those things you can able to see very clearly, or very in a close examination you can able to see in the glottal activity. Whereas that is masked in the case of speech signal and all. If you want to look at those details at a speech level, it will be masked. That means the other things will dominate, because the actual sound details and other details will be dominate, like emotions and all those things will be dominate. That's the problem.
And sir, what is the possibility of applying some deep learning technique in identifying those kind of anomalies? Because you told that just
Yeah,
like
yeah.
two,
Even
three
even
seconds.
we have done that one actually. That is not we are not play. It's not the part of the PhD work, but we ourselves carried out on the CG signal, whatever is captured, or in the speech signal itself. Using a deep learning techniques, you can able to find out the GCI and GOI and all. That means by using, we are taking the normal speech and the inverse version of that one, and then taking just a raw signal itself directly by applying to a convolutional neural network at multiple phases and all. Then we got the people are observed the GC and GOI locations very accurately and all. Yeah, even that is there in one of the our interspeech papers was there. In that, by using deep learning, people have estimated that one and all. Can do that, but the problem is that getting that much of like data and all, that is question mark. But still you can do it, because anyway you are taking for every sample, you are getting an example frame and all, so that way you can get enough data and all. Yeah, we had done, we made some attempt and all. Yeah, it's working fine. You can use
Thank
that.
you, sir.
You can use that, but for the at a grosser classification level and all. But if you want to examine very close details, like suppose for example you have a vocal disorder, and afterwards the patient is taking the treatment and all, and if you want to see that how he is recovering and all, so all those details if you want to see, like almost like in a weekly manner and all, so it will be nice. You can able to analyze the glottal activity that was captured through EGG device. And not only that, people are using both the ways, both the modalities. One I told you EGG, and the other one is that capturing the vocal folds behavior, vocal folds characteristics through video also. Like that is going to be like invasive technique, like keeping a camera in your glottal, like, and then recording the signal and all. So that is a bit of painful, but still you will get a more accurate thing. And now you can able to club these two modalities and all, EGG and as well as that also. And then you can able to get more accurate analysis. You can able to observe that. And what we are doing is that instead of keeping a camera inside and all, since it is very painful and all, we can able to we are able to simulating the glottal activity by using the phase information and all. That's what we attempted in the MS work and all, because we captured the phase properly, and the phase is nothing but actually the way the vocal folds vibrates. Then the phase will change very accurately along with the vocal folds vibration and all. And once you have the phase information and the amplitude information, then you can able to, by using some 3D, you can able to simulate the vocal folds and vocal fold activity, and that can be observed, that can be shown to the doctor. And initially doctors will be difficult because they used to see a real vocal folds vibration, no? So later on, by applying certain training and all, then the doctors also will get used to that. And that is not better. What I'm saying is, instead of keeping the stroboscope or like a camera inside your glottis, that is a very painful and like no lot of technical help. Technicians, good technicians are required. All these things can be avoided by using these simulations and all. What we can able to simulate the vocal fold activity. That's what we have done in the telemedicine applications and all. You can use that. One can use that. Yeah.
Okay, sir. Thank you very much.
Yeah. Thank you.
Dr. Udit, do you want to add anything?
So, okay, sir. So you have actually used Gaussian noise for determining the GCI and GO activity. So, but when we record EEG in real time, there may be a movement of necks. So that may introduce some motion artifacts in that. So that mix with the EEG signal.
Yeah, that's what that motion. Yeah, that's what I'm saying. That motion is like when you are moving the neck also. That movement is a low frequency content actually. That is a low frequency with respect to the vocal folds vibration, the rate of vibration, the movement of the neck. Not only the movement of neck, even sometimes you are swallowing or you do certain things actually at because certain reasons. At that time, the muzzle movements also will take place, and they also will introduce the noise and all. So all those things actually, when we compared that with respect to by adding this Gaussian noise and all, so they appears like overall the characteristics when you look at the spectral details or these details and all, appears to be like a close to that, close to the way of the Gaussian noise. When you add that one, the frequency domain related details and all those things also close to that. So that's why we approximated, we mentioned that when you're carrying out experiments and all, we have added the Gaussian noise of different magnitudes, different magnitudes, so that it assuming that a similar kind of noise will be there when you're collecting the EEG signal also.
So what is the general frequency range of EEG signal?
EEG frequency of EEG signal is this one, the vocal folds vibration. No, that was the fundamental frequency, and then the other frequency is that sudden discontinuities will be there, no, closing phase and opening phase. So the closing phase is that actually you see that how narrow the closing phase, the corresponding frequency will be reflected in the frequency domain also. So that kind of a thing. So there are high frequency components will be there, but the dominant frequencies will be not that high as in case of speech and all.
Okay, sir. Thank you, sir.
Okay.
Thank you for the informative time. Yeah.
Okay. Thank you. Yeah.
Hello.
Thank you. Then yeah. Thank you.
One question is there from Ritu Joy.
Sir, just one question.
Yeah. Tell me, please.
Sir, I wanted to know if it's possible to translate this work, what you've done, to from you've taken the fundamental frequencies and detected the abnormalities in the glottis. So, would it be possible if we translated this work to formants, and since formants are nothing but shaping of the glottal pulses by the upper vocal tract, so is it possible to use those formants to detect abnormalities in the vocal tract, because since the fundamental frequencies were doing that for the glottis?
No. What I know is that actually the formats, as you said, those are the resonances, the dominant resonances. Those are imposed by the vocal tract, right?
Yes, sir. Yes, sir.
But the vocal folds are behind that, and I'm not very sure actually here that particular the fundamental resonances actually, because those resonance, if you look at a frequency domain, the formats are like at a range of the higher level, like you can say at the first format will be around
1
500-600,
kilohertz.
yeah, 1
Around 1
kilohertz
kilohertz. Yes, sir.
at that time and all. But here in the case of these vocal folds vibration and all, so you can see that the vibrations are at the Glottal Cycle range is about it's kind of a pitch cycle and all,
Yes,
right?
sir.
And pitch cycle, and the changes in this, basically the closing phase, the characterizing the closing phase, that is very important.
Yes, sir.
So the characterizing of closing phase is nothing but sudden. Actually, it's like till that point, the signal is slowly, somewhat with varying with certain linear way. And at the time of closing, because of that, you can see a sudden change will be there. So
Okay.
that is nothing but your the closing instant and all. That's what we are looking at. That's what we are identifying that as a closing instant and all. But I'm not very sure actually how these we can view this. That what I want, what you want to say, that in that formats, is there any change that is due to these abnormalities?
Yes, sir. Yes, sir.
That I'm not. Yeah, that will be there definitely, because because this change, this closing phase, the abruptness of closing phase, that depends on a speaker also. Like speaker to speaker, it varies and all, and then even the sounds also, for different sounds also, you can able to control. Because that you involuntarily you will do that for different sounds. If you try to analyze this closing phase and all, that will be definitely, you can see some changes and all. But I don't know in case of format frequencies whether that change will be reflected or can be observable or not. That I have not done, but someone can able to see that, can able to examine that, and at least, yeah, you can do that, because usually this glottis will be analyzed by uttering only the basic vowels and all. Like, so that way you can able to analyze the vowels, and you can able to see that. Uh, like for different cases, when you analyze that for different people, so what changes here, how much the format changes, or how they are changing, and all, one can able to see that. But you need to have very close very keen observations or keen analysis is required for that and all.
Okay. Thank you, sir.
And able to
Okay,
do
thank you,
that
sir.
actually, but we need to, somebody has to very look into very carefully and very accurate way you have to do that. Okay, yeah.
Thank you, sir.
Thank you very much. So yeah, if there is no questions, then I'm just closing the presentation
Yes, sir.
slides. Okay, and yeah, okay, then can I leave?
So thank you, sir, for the
Thank you,
presentation. So
sir.
Yeah,
before
thank you.
that,
Yeah.
we would like to take a screenshot with all the participants. So the participants are requested to turn on the videos. So
Okay.
you can take a screenshot.
Oh, acha.
You can unshare, sir, if you want to unshare. So other participants are also coming. Okay. Yeah, it's fine, sir. Thank you, sir. Thank you very
Thank
much.
you, sir.
Yeah.
Thank you
Yeah,
very much, sir.
yeah, thank you very much. Thanks. So now I'm leaving. Thank you. Yeah, thanks to the organizers, yeah, Udit and your team for organizing this workshop and inviting me for this occasion. Thank you very much. So where to, how to leave this?
So dear participants, we will meet tomorrow for the next session. So now the session is end for today. Thank you all.